Okay, so this is where we ended the last day. Before I get down to business, though, I would like to go through the long multiplication thing. Okay, that's why I haven't brought the screen down here, because I want to go and do the long multiplication thing on the board. A second here. So we just go through it on the board here for a little while. Now, what I was asking you to do was 32 by 32 multiplication to give a 64-bit result. And I use the analogy, okay, which I know the analogy and the thing it was analogizing were so close together that many of you conflated the two things. However, the analogy I used was that if you had two single-digit numbers that you had to multiply together, you know what single-digit multiplication is because you have the times tables in your head, and you can use an algorithm to combine that single-digit multiplication ability that you might have to do multi-digit multiplication. A long multiplication was the algorithm. It was called that in my time anyway. And basically what you did was you took the least significant two digits, multiplied them together. You took the less significant digit in one case with the more significant digit in the other, 63, and you shifted them to the left by one digit position because one of the digits was already shifted to the left. And you did the same thing again. 6 4 is 24, shifted to the left by one digit position, and then 6 9 is 54, shifted to the left by two digit positions. So you got four partial results and you have to combine. Okay, that's long multiplication. Now, so what I was saying was, by analogy, we want to multiply a long word by a long word to produce, let's call it a quad word. That's by analogy. Okay? And by analogy with single-digit multiplication, which you guys have in your head, and me too, I was saying that there is word multiplication built into the silicon of the 68,000. So I was saying word multiplication on the 68,000 is equivalent of your times tables. You have to combine it in an algorithm, long multiplication, in order to be able to do long word multiplication to produce a quad word result. So that was the analogy that I was using. Okay, so with that in mind then, if we have a situation like this, where we have two long words to multiply together, okay? Two long words to multiply together, and we want to produce a quad word result. Okay, now what I was proposing was that if we call this guy here U, and this guy here V, and the result here R, okay? Just so that we have a nice handy name for them. Okay? Everybody got their, whatever it is, links, deodorant, whatever it is on. We just keep moving. If we take these two things together, we want to get this as well. If we call this U and V, then we can talk about this part here as UH, and this as UL for high and low, VH, VL. And it's a bit more complicated for here. You could have RHH and RHL and RLH and RL kind of stuff, which we're not going to bother with. Okay, so what we need to do is to generate the partial results in the way analogous to the long multiplication of two-digit numbers. And how we would do it is we would calculate, okay, so that's what we have to begin with. I'm going to run out of space here a little bit. We're going to multiply UL by VL, and that'll be one of our partial results. Okay, UL times VL. So we're multiplying the two less significant digits together in the analogy. We're going to multiply VL here by UH. Okay, and because that's shifted over to that by 16-digit positions or a word, we're going to shift the result over by 16-bit positions or a word. And this will be VL times UH. Okay. Similarly, we're going to calculate this word here, VH multiplied by UL. And we're going to shift that over by 16-bit positions. And finally, we're going to multiply the upper word of VH, with the upper word of UH, and we're going to calculate that to be VH times UH. Okay? And that, logically speaking, in the result, in the 64-bit result, will be shifted over by 32 bits in order to slot it into position. Now, all these partial results are generated by 16-bit by 16-bit multiplication to produce 32-bit results. The difficulty arises when we go to combine. Okay? We have a multiply instruction for that. Now, so I made the observation the last day that if you imagined that you were writing, and we haven't done this yet, of course, a function, then one of the nice things about a function is that you pass information to the function and get information back from the function in a kind of an orderly way. So typically you'd use the register starting in D0. So what I'd be suggesting is that we use D0 for this guy here and D1 for this here. We're not going to write a function, but let's just pretend we're going towards a function. So D0 and D1, that would be the information going to this piece of code, and the information that it would give back would be D2, D3. Okay? So what we're saying, so I'm just suggesting that would be nice. I'm also suggesting that we want to make it fast, so we would like to avoid using memory locations to hold stuff, if possible, because access to memory is relatively expensive. Now, one of you, who's here, where is he? Did a cycle count test. Mr. Aslet, is that right? Yes. And we'll talk about that in a few minutes. Or at least he can talk about that in a few minutes. So we want to make it as fast as we can. So that means we should try and keep these things in registers if we possibly can. So I've done this, and I've actually done it in a program that has been used for many years, and I don't think it's. I think the multiplication part of it is right. Let's put it like that. So now I just have to find where I put the diagram that I had. Hack the right book even. Give me a moment here. Uh-oh. 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 Oh dear. Okay, enough of the singing. I'm just going to have to remember. Okay, so what I'm suggesting then is we have D0, D1, D2 and D3 are in use. So let's say we calculate this guy here into D3. Okay, so D3 is we're already suggesting we're going to have D3 in use for the lower long word of the 64-bit result. I'm making the observation that this word part of D3 is going to find its way into the actual result without any further changes. Okay, so there's no particular issue there. So if we say D3 for that, if we similarly say, although it's not quite as clear cut here, D2 for this one here, because the upper word of D2 is going to find its way almost unscathed into the result here. Okay, there may be some carries into it. Okay, that's the only change to be. So we have D2 for UH times VH. We have D3 for UL times VL. So let's use D4 for this and D5 for this. Okay. So I'm trying to map out how I'm going to be using. Now, I'm definitely going to be using the add with extend instruction. When you look at the add with extend instruction in your instruction set summary, what you'll find is that it requires either both operands to be in data registers, or both operands to be addressed using address register indirect with predecrement, which is an addressing mode that we haven't looked at all yet. Okay, so we're going to be stuck with using the version of add with extend where the two operands are in data registers. So if I want to add just the value of the extend bit into something, I'm going to have to put 0 into a register and use that register as part of the add with extend. So I'm going to say, I'm going to use D6 to hold the value 0. Right? So I've got one spare register, which it turns out, as far as I can remember, I don't actually need. One spare data register. So this is my map. Okay? So I want to produce all these partial results into those locations, and then we'll see how to combine them. So this might be slightly different in terms of which registers I use to what I showed you earlier. Okay? So we want to get UL times VL into D3. So we could begin and we could say, well, we better move D1, say, into D3. Okay, now we could move long all of D1 into D3, or we could move just the word part of it. We're only going to be using the word part of it, but the fact is that the cost difference, well, we're going to use the word. There's no cost difference in the 68,000. I move long and I move W between registers takes the same amount of time. Okay, so we'll multiply unsigned D0 into D3. So we've got UL times VL now in D3. Okay. Now let's copy. I'm going to copy V. Let me just think about this for a second. I want to minimize the amount of switching and swapping that I do. I can't do that. Okay. So I'm going to move the word. Okay, so what I want to get now is VL times UH. Okay, so I move D1 again into D4. I'm going to swap D0. So D0 now has UH in the right-hand part, the right-hand part, and UL in the left-hand part. So I'm going to multiply D0 into D4. So I should get UH times VL. So I've got that. Now, why don't I go for UH times VH? Because I have U already switched around. So if I copy D1 into D2 and swap D2, so I have VH in D2, I have UH in D0, so I just multiply D0 into D2, so I have that one, and now anyway, I'm going to have to swap back D0. There's definitely a trick that you can play here, which I'm not actually succeeding in doing.
Maybe swap D1.
Here. Yeah. Before I move it. Okay. I'm going to get confused now, right? Swap D1. Okay. Move long D1 into D2 and multiply it. Okay, so now in D1 I have VH, thank you, which is what I want. In D0 I have UH, but I actually want UL, so I swap it back. Now I have UL. I move D0 into D5. Multiply D1 into D5, so I have VH times UL, and then finally swap back D1 so that U and V is D0 and D1 as they were before. Okay? People agree with that? Yeah? Okay, so we have the four partial products that we want, four partial results, I should say, that we want. Now we have to combine them. And we have to be right. There's no use getting this half right or a quarter right or right sometimes, or right for small numbers, you know? That's worse than useless. Right? Worse than useless because it's the kind of code that would work some of the time, you know, your worst nightmare. You know, oh yeah, there's a fault in it, and we bring it to the dentist and the pain goes away, you know, that kind of problem. Much worse than useless. Okay, so here is what I am going to do. I know that this thing here doesn't need to be fixed up. That is, the rightmost word of the result needs no further processing because there's no carries into it or anything like that kind of thing. So I don't have to bother with it. I'm going to mess around with D3 now, but the messing around is not going to change the value that's there. I'm going to put it up into the upper half of it actually, but I'm not going to affect it at all. And when I'm finished foostering, I'll switch it back. Okay. What I want to get at is these pieces here. I want to add the top part of what's in D3 to the bottom half of what's in D4, and I want to worry about whatever carry might occur from that, because a carry may occur. I don't want to lose it. I want this thing to be right all the time. Okay. I also then want to add the sum of those two things to the word part of this, and I want to worry about the carry that results from there as well. Okay. So I've got a problem there. The way I'm going to, I'll take your point in just a second. The way I'm going to attack it is I'm going to switch these two halves around so that the upper half of D3 becomes its lower half. And I can add the lower half of D3 to the lower half of this, worry about the carry. Add the lower half of D5 to the result of that, worry about the carry. And then I'm out of there. Okay, then I have to move on to here. Yes, sir?
I just remembered, yeah, D1 is D2 there.
When I moved D1 into D2 there, I could have moved just a word. Yeah. Once again, the cost, as it happens in the 68, this one here, right? The cost of the 68,000 of moving long words between registers in the processor is the same as moving words or bytes. Because it's got full 32-bit wide data paths for moving stuff around. Okay. Consistency is the hobgoblin of the simple mind. What's this young man's name is? I'll think of his name in a while. Emerson said. Yeah. Said a lot of things. Okay, so let's write the code for this. So now we're combining the results. So maybe we should put in a little comment. Okay, so the first thing I'm going to do is I'm going to swap D3. Now swapping D3, remember, swap just switches the two halves of the register. It's fast and it's non-destructive. Okay, and so I can swap them back later and back to the original. Okay, so swap them. Now I'm going to do this. I'm going to say I want to add dot W. Okay. Well, let me just add D4 into D3. Okay? So now, what I'm doing is I'm taking the word part of this and what was the upper word of D3, which is now in the lower part of D3 because I just swapped them over. Okay? Now remember, a couple of things. There's a couple of things to remember here. When you operate on a word, the word part of the register is always the right-hand word, and it has no effect whatever on the upper word or the other word. Okay? It's strictly word-oriented. Even if there's a carry or a borrow, it does not propagate up into the upper half at all. It's as if the upper half didn't exist. And any of the bits and any of the values that are in the upper half, say here, are not affected whatever by this. So it's just what we want. That's the first thing to remember. And that's the way with all instructions on the 68,000, apart from multiplying and dividing. Second thing to remember is that, and this is going to come up, and it's come up a few times, the condition code register has these 5 bits, X, Z, Z, B, C. They all have values all the time. If you want to make use of them, for something, you have to make sure that they have a value that you're interested in, and that you have previously calculated in a way that you want. It's not that they'll be 0 or that they forget anything or any of that kind of stuff. You have to make sure that if you're using their values for some purpose, the values have been set by you, like initializing a variable. You have to make sure that they have a sensible value in. Here, I'm using the add instruction, which does not use any of the bits of the condition code register at all. Okay? It does set them, but it doesn't use them. Right? So this is the starting point. I'm just going to add those two numbers together. The next thing I'm going to do, oh, I forgot something. Let me just put in an instruction here. I'm going to clear D6. There's the possibility that when I added these two words together, there's a carry. Okay? And that'll be copied into the condition code register into both the C bit and the X bit. The X bit is the one we're interested in. And so the situation here is now, there could have been a carry from adding these two. And what I'm going to do an end run around all this mess in here. I'm going to add that carry bit's value, the X bit's value, either a 0 or a 1. I'm going to add it in here. Why not? Okay, it's completely legitimate. I'm just going to add it in here. And the way I'm going to add it in there is I'm going to say add with extend long D6, which has the value 0 in it. So I'm going to be adding nothing but the X bit into D2. So I could say there, account for the carry. Account for the carry that may have resulted from adding D4 into D3. Okay?
What happens if there's a carry down here?
Down here?
When you add the, we'll do the after extend one to the carry by doing that after extend.
Not sure I understand the question. Okay, so I've added, let me just get a bit of chalk here. So I've added these two things, right? I've added those two things effectively, right?
Yeah.
Possibly got a carry, and I added the carry in there, right? Now, let me just add the next piece, okay? Maybe it might answer the question. So I'm now going to, so now I have to, you see, overall I have these three things together. So I've added two of them together. The sum of them is in there, is in here. I'm going to add this one into it now, right? So I'm going to say add .wd5 into d3. And also, okay, now, this instruction here is add, just like the first add there, it does not make use of the X bit. Maybe that answers your question, I don't know. It does not look back at the outcome of this calculation here, because it's just a straightforward add, it's not add, it's extend. So it will be a generator of an X bit and a C bit, but it won't consume it. It isn't taking it into account. Can I just write this down first and then, before I forget, account for the carry.
Yeah, I think the question was when you add the carry bit into D2,
yeah.
What if it overflows?
What if it overflows up here?
It's a long, yeah.
Oh.
No, because you've added an extended long word, it can't overflow.
Yeah, very good question, and thanks for clarifying it. Really good question. The question is, if you add a 1 in here, it's going to either be a 0 or a 1. Is it, and we're adding it into whatever happens to be in D2, is it not possible that there could be an overflow or carry out from here? Is that right? Yeah, something like that. Now, are you an engineer or mathematician? MC68000. Oh, God. Okay. Okay, mathematicians, people with the analytical turns of minds, and engineers maybe, because you're usually good at maths, and emphasis people even. Is that a sensible question? Okay, now I don't mean, I'm not being funny or flippant, but is it a sensible question? And if it is, what's the answer to the question? And if it isn't, why is it not a sensible question?
If you're only adding if you had done an add with extend with only on a word, then it's a sensible question. But
Yeah.
when you did a long word.
But I mean, is it not possible that you could have all ones there?
When you multiply two numbers together, the number that you get out is the sum of the digits of the number. Like if you had multiplied two-digit numbers, the one you get out is going to be bigger than 4.
Yeah, yeah. Is that what you were kind of working at? The thing is that we know that if you multiply two long words together, the result has to fit into a quad word, no matter what. Okay? And so that means that if all of these add up to the result, like we're talking about unsigned arithmetic, I can't figure out signed arithmetic at the moment in this connection, but if it's unsigned arithmetic, that means we're guaranteed that there'll never be overflow or carry out here. But that's by analysis, that's not by looking at it and thinking in terms of coding. That's by thinking about the if I may say, the theoretical side of it. Okay? So it's a very good question to ask, but the question itself, it can be disposed of by thinking about the overall situation. And there'll be many situations like that in this in writing programs like this. Okay? By an analytical take on the overall situation, you may be able to avoid some problems. And that's why, if I may say, mathematicians and MSIS people are particularly welcome in this course, because they're disposed to looking at something a bit more analytically than engineers. No offence. I'm an engineer myself. And by the way, engineers are disposed to thinking more analytically than computer science students. Okay? So it's very important to use your mathematical, analytical abilities to look at these problems from a bit of a distance rather than jump in like a lot of computer science people do and just hack around and hope it works. Okay? So enough of the preaching. Okay, so we've dispensed with we've fully calculated this guy here, and we fully calculated this guy here. Now we have to calculate the sum of the top half of this with the top half of this with all this. We've got to calculate that. And I'm going to play another dirty trick here because I'm finished here, I don't need these values anymore, those two values in particular. So I go to 0, right? So I'm going to say here D4, and I'm going to clear D5. Clear is the same as move 0 into, by the way. And then I'm going to swap them. And I'm going to swap D5. Okay, so now what I have is what was the upper word of D4 is now aligned in the lower part of it. What was the upper word of D5 is now aligned in the bottom part of it. And the upper part of D4 has got 0 in it, and the upper part of D5 has got 0 in it. So I can just add that as a long word to this, and I can add that as a long word to this. And by going back to the argument or the discussion we just had there, we don't have to worry about overflow at all. So all we have to do now is just simply say add .l d4 into d2, add .l d5 into d2, and that's it, finished. Okay? We have to swap d3, and I'd be wondering why that rocket kept crashing, you know? Maybe because I'd forgotten to put in that instruction. Thank you very much. So to swap D3, to get the rightmost words, the least significant words, back in alignment. Thank you. Okay? So, yes, sir?
Will move quick assume a long word?
Yes, move quick always assumes a long word. It's rather unusual instruction. It's in the slides. It always assumes a long word. It takes the 8-bit value that you specify and sign extends it up to 32 bits and puts it into the leader. Say again? Would clear and move quick would be of the same speed. Yeah, probably would. Yeah. You could use clear.l. I'll be telling you about how to calculate speeds later. Okay? Now, one of you. Okay, so this is a way of using 16-bit multiply to do 32-bit multiplication, combined in long multiplication. The classic way to implement multiplication on a machine that has no multiplication instructions at all is a combination of repeated shifting and adding. Okay? And one of you, at least one of you, implemented that in assembly language. Okay? Used shift instructions and add instructions, or shift, possibly rotate instructions and add instructions, and wrote a program to emulate that, to do that in assembly language code. Would you like just to say what the speed difference was?
That 6 times
It was about 6 times slower. He ran it on an emulator which counted the number of cycles, of bus cycles, that the code required to run. And according to the emulation, the clock timing was about 6 times slower. Okay? So this will be a little bit faster. Okay? We'll come back to timing later, but it's an interesting result. Okay? Any questions about that? There's a bit of virtuoso stuff in this. I mean, when I wrote this took me quite a while to write and to minimize the number of movements of data and all that kind of stuff, right? And I tried lots of different ways, you know, could I use add with extend on words or on bytes and stuff like that. And it's a very tedious process. And what you see, I hope it's right, what you see is the result of quite a bit of work. And I'm sure you found it was, maybe still finding it difficult to do that kind of thing. But don't give up. Don't give up on this stuff. It's no good if it only half works.
Is there a big difference between adding words and long?
Is there a speed difference between adding words and long words? Well, if the operands that you're adding are all in the processor, there's no speed difference. No. But if you're adding, say, an immediate value that's out as part of the instruction, well, that immediate value has to be fetched. And if it's a word or a byte, it'll take 1 bus cycle, and if it's a long word, it'll take 2. So it'll be a bit longer if it's long. Okay? But I will show you how to manually calculate that, approximately anyway, so you can work out for yourself what are the best instructions. Okay. So who said this isn't exciting? Now, so we're back to looking at what we're looking at is how you do control the program flow. So we've looked at it informally, indeed we've looked at it a bit formally, but we have to try and get a sort of a fairly strong grip on it so that when you're at home and you're trying to work out how do you do that again, you'll be able to figure this stuff out, not just remember it, but actually figure it out. Okay, so we're looking at the condition code register, which is part of the status register there. The bits of interest are XFZVC. The other 3 bits, by the way, are reserved by Motorola, or they were reserved by Motorola for future expansion. And I don't know whether any of them are used in the 68020 or 30. I just can't remember. The system byte, there are 5 bits of interest in that, which we'll talk about in due course. And I did see in somebody's book that the condition code register is sometimes called the user byte, which is an odd name. But anyway, it's all a bit odd, I suppose. Okay, so they're the conditions. And remember, these conditions are conditions that operate on the bits in the condition code register. Okay, so when they're talking there about n, it's the n bit of the CCR that we're talking about. And that mi there minus, that condition is true if the n bit is true. PL there plus is going to be true, that condition will be true if the n bit in the condition code register is false. So that's how it works. And you choose these to suit yourself. You choose to use these conditions as parts of conditional branch instructions or other instructions to suit the purposes that you have in mind. For instance, suppose you have 2 numbers and you add them together, right? 2 bytes and you add them together. And the result of adding them together has the most significant bit equal to 1. Most significant bit of the byte equal to 1. Having added them together, the n bit will be set. Okay? But it doesn't mean, and so at the machine level you might say, well, that means the numbers are negative. But they're not negative necessarily. It depends on how you, when you're writing the program, are interpreting them. If you're interpreting them as unsigned numbers, then you simply ignore the fact that the n bit is set. Okay? You just say, well, I'm not dealing with signed arithmetic, therefore the n bit has no particular meaning, nor does the v bit, the overflow bit. They're just of no meaning, and so I won't use any conditional branch instructions that have them as part of their conditions. Okay, so there's tutorial 4, right. Okay, so we're back to we're back to flies here. So we know that you can construct a conditional branch instruction. You could say branch any, branch if not equal, branch in other words if the z bit is 0. You could say BEQ, you could say BMI, branch if minus, BPL, branch if plus, and so on. By the way, plus includes 0. 0 is a positive number, remember. Okay? So if you can have these conditional branches, you have to set up the conditions that they branch on. And that's what we're talking about here. How do you set up or calculate, cause the machine to calculate conditions and put them in the condition code register? Well, it's a property of every complex instruction set computer, as I said before, that it has that many or most of its instructions will have an effect on the condition code register. If it was a RISC machine, most RISC machine instructions will not have any effect on the condition code register. You'll have to explicitly use instructions that set either the condition code register or maybe one of many condition code registers in some RISC machines. But anyway, in 68000, if you look at your instruction set summary, you'll find that a great number of the instructions have an effect on the I beg your pardon, that many instructions will have an effect on the condition code register bits. One of them is the move instruction, right? If you look at the move instruction in your instruction set summaries, you'll find that it affects the condition code register as you might expect. You see the asterisk. When you see an asterisk in the condition code register summary for an instruction, it means that the bit, that particular bit, let's say the n bit or the z bit, is affected as you'd expect, and as you'd expect we'll talk about in a minute. And minus means the bit is unaffected. It retains its previous value. And there's 0 and 1, and there's U for undefined, okay? Left as an exercise to the reader there. Okay. So, here we are, XNZVC. Okay, the X is the extend bit, okay? And it's essentially the carry bit's slower brother, right? It's the same as the carry bit, but it's not affected by all the instructions that affect the carry bit. It's only affected by what Motorola are pleased to call the arithmetic instructions. And I never know which are arithmetic instructions and which aren't, so I'm left to actually looking at the instruction set summary to make sure that a particular instruction may have an effect on the X bit if I want it to have it. Okay? N is the negative bit. It's set if the result of whatever, say, add or subtract or move or something like that is negative. And negative means that the most significant bit is set. Essentially, that's what it comes down to. Because that's the signifier, if you remember, if you're dealing with signed arithmetic, the most significant bit is set, it means the number is negative, okay, in 2's complement form. Z is a 0 bit, set if the result of the operation is 0 and cleared otherwise. Now I've put in this cleared otherwise everywhere because again, you need to be aware that the condition code register bits really are very ephemeral. They only really refer to the immediate past, they don't go back very far at all. The present and the immediate past. Okay? Z bit, the V bit is the overflow bit, which will be set if sign overflow has occurred. If you add two positive numbers and get a negative result, that's sign overflow. Okay? You only pay attention to it, of course, if the things you're adding in that example are indeed signed. If they're not signed, you just ignore it. The carry, the C bit is the carry borrow bit. Set if there's been an arithmetic carry or borrow, and clear the bit. Okay, so they're the expected interpretations or meanings of the condition code register bits. Now, if you look at the move instruction, which is a very commonly used instruction, most versions of the move instruction affects the condition code register, and they affect it in this way. You just think about it. Say move. You're saying you're moving something from here to there, from one place to another. The condition code register is set according to the value of the thing that's moved. If the thing that's moved is 0, the Z bit will be set afterwards. If the thing that's moved could be considered negative, if the most significant bit is set, the N bit will be set. Okay? If you look at the instruction set summary, unfortunately, I don't have one in front of me here, but if you look at the instruction set summary, you'll see it. Okay? Now that means that in our example code this morning, there was one instruction we didn't need. Now, if anyone has taken it down, you might be able to identify it. There was one instruction we did not need. Okay, there was a compare instruction. You'll remember the piece of code I'm thinking of. The piece of code that I'm thinking of was this. We had move a byte from A0 into, was it D1, was it? I think it was D1, okay? And then we had compare the byte with 0. Okay, and then branch if the Z bit was set to finish. I think that was what we had written down. Okay? Now it turns out that this instruction here is not needed because this instruction will have already set the condition code register according to the value of the thing that was transported, the thing that was moved. If the thing that was moved was a byte whose value is 0, the Z bit would have been set here. So we don't need this instruction at all. Okay? We can just leave it out. Okay, you can omit that instruction. Now, because that instruction is outside a big loop, it's not going to make a hell of a lot of difference. But you might as well remove it. Remove those kind of instructions where you can. Okay, so you need to, when you're looking to do something in the 68000 or any other machine like that, you need to figure out what operation you want. Is it move or multiply or whatever? You need to figure out what addressing modes are available, okay, and where the data is and all that kind of stuff. And you may also have to figure out what effect it may have on the condition code register. So you have a number of things to juggle when you're selecting instructions to perform your set of operations. And it takes a good bit of time and you need a fair bit of skill to do that. Okay, can anybody say, maybe I already told you, but can anybody say why you might imagine that a RISC machine has this feature that most instructions do not affect the condition code register? Why do you think that would be the case? Because it is the case. Well, it's slower. Yeah, why would it be slower? Well, you're certainly affecting every bit at every second. So I mean, there's the actual overhead of actually moving, turning on and off the latches and so on. But do you remember I was saying that in many modern machines you have these pipelines, right? Where you're executing this instruction, but you're also partly executing the next instruction, and maybe executing a bit of the one after it, speculatively. If you're executing an instruction now which sets the condition code register, and if the next instruction might depend on the condition code register, it means that this instruction has to complete before the next instruction can get very far. So if the assumption is that the condition code register is being affected by an instruction, you have to slow the pipeline down to allow the effects to be posted to the condition code register before you can even partially execute the next instruction. If you remove that assumption and say that no instruction affects the condition code register unless you explicitly look for it, then the succeeding instructions which are being partially executed don't need to wait for the condition codes to be posted. So that's a big reason for not having condition code registers affected by every instruction in a RISC machine. Okay. Can we move on? There are some instructions in the 68000. Oh, sorry. Yes, sir.
Does that mean that the zero flag is set wherever an register is equal to 0?
Sorry, just to go back here, does it mean that, say, the 0 bit there is set any time a register is put to 0? Not quite. You really do have to study the instruction set summary very carefully. So, for instance, I think if you move something into the data register, then the condition code register is set, as you're suggesting. If you move something into an address register, I'm pretty sure it's not. You need to look at the instruction set summary very carefully. Okay? And it's part of, as I was just saying, it has to be part of your consideration. Which instruction am I going to use? Where am I going to put the data? And so on. Okay. So there are some instructions that have no effect at all. I was going to use a very rude analogy, but I thought I'd better not when being recorded. But they have absolutely no effect at all. So you have an instruction which doesn't do anything at all except it may set up the condition code register. It may calculate a condition and post it in the condition code register so that you can use it later. And some of those are the compare instruction, which we started talking about at the end of the last day, and then two other ones that I just thought of: test, which is compare with 0, and BTST, bit test, which we'll talk a little bit about. And these instructions, it's not really true to say they do nothing, but they don't result in result, say, in a data register or an address register or a memory or anything like that. All they do is they set up the condition code register. So compare instructions. So there's an example there, right, of an instruction that has no effect other than to set up the condition code register with a calculation. Okay, so once again, you're going to use a conditional branch instruction. You have to make sure that what precedes it sets it up according to the condition it is that you want to test, if you'll forgive my English. Okay, so just a quick look at a couple of these instructions. The compare instruction, it's exactly like a subtract instruction, but it does not replace the second operand of the result. So it throws away the result, puts the calculation, sets the condition code register according to the result, and then discards the result. Very useful. We used it this morning. So what I said there, it sets the condition code register as if the first operand had been subtracted from the second. Actually, it did subtract them, but it just threw away the result. Test. I'm a little bit dubious about saying this, but it's somewhat equivalent to compare with 0. Now, you want to look at the condition code register because it may not affect all the bits that compare does. So here's bit test. There's a bit more to bit test than meets the eye. There's a family of them. There's a bunch of them. Bit test, bit set, bit clear, and bit change. Okay? A bit test is the only one of these that does nothing in the sense that I meant. Okay? It basically checks the bit that you specify. We'll have a look at it the next day. You specify a bit in a particular place. If the bit is 0, it sets the Z to 1. If the bit is 1, it sets the Z bit in the condition code register to 0. Okay, that's all, folks. Thanks for your time as ever. We'll see you next week.